Today I will talk about a work joined with Achim Jung while I was Mary Skłodowska-Curie Fellowship at the University of Birmingham. And this work, I felt the desire to develop it while I was working at certain generalization of stone duality. However, since not all of us may be familiar with stone duality, I try to approach the matter again from an independent perspective. And in particular, what I want to emphasize at first is that there is a sort of symmetry between open and topological spaces, between open sets and compact saturated sets. Okay, actually, a saturated set is an intersection of open sets, but in T1 spaces, so for example, in Hausdorff spaces, every subset is saturated. So you might just think of compact sets and think about Hausdorff spaces. So there's a symmetry between open sets and compact sets. Let's see some examples of symmetry. Okay. So let's start with the definition of local compactness. There are different definitions that are equivalent for Hausdorff spaces. My favorite one is the following. So if you have a compact subspace, compact subspace K, and an open subspace U, such that the compact is containing the open, then local compactness says that there are an open set U prime and a compact set K prime, such that we have this box. K is containing U prime, containing K prime, containing U. For other spaces, this is equivalent to maybe what is more familiar, like every point has a compact neighborhood. But this is the definition that appears, for example, in some books where they consider also spaces that are not Hausdorff. Okay, let us write the definition. Here, compact, we have a compact and open, and a compact containing an open. Then there are open and compact such that we have this chain. And now what happens if we swap open and compact, and we swap inclusion with reverse inclusion? Well, here, now instead of a compact, we have an open, instead of an open, a compact. And here, the reverse inclusion says that the open contains the compact. And then you get compact and open. And we have that what is now a compact is containing the open, is containing the compact, which is containing the open. So actually, you get the same property. Okay? So you see that already the definition of local compactness, which is important in our topology, has this symmetry between openness and compactness. Okay, let's take a locally compact Hausdorff space, and let's look at the so-called Wilker's conditions. There are two. Let's look at the first one. You have a compact set K, and you suppose that you have two open sets that cover the compact sets. Now, in a locally compact Hausdorff space, what you can do is that Wilker's condition tells you that you can cover the compact K with two compact sets, such that the first compact is containing the first open, and the second compact is containing the second open. Okay, but now what happens if we swap compact with opens and we invert all order theoretic notions? Actually, we get a statement that still holds in all locally compact Hausdorff spaces. here. So now, instead of having a compact contained in a union of open, we swap things around and we have an open that contains the intersection of two compacts. And then if you just symmetrize this, you'll get the existence of two open sets, 1v2, such that vi contains ki, and instead of having a compact containing the union, U contains the intersection of V1 and V2. Okay, and also this property holds locally in all locally compact Howell spaces. So maybe one can ask, okay, but could we deduce one from the other? Would be good if we could have two theorems at the price of one. If there were some actually formal symmetry between open and compact. Okay, just as an analogy, this is just an analogy. Think in category theory, if you prove a statement for all categories, like if you prove that a category with products and equalizers has all limits, then you automatically know a dual statement that if a category has co-products, equalizers, then it has all co-limits. Let's say you can deduce it from here, or you know that a proof will be symmetrical, will be very similar. And this is possible to get these two theorems at the price of one, because for every category you have another category, the opposite category, where everything is inverted. And what would be good in our setting is the following. If we have a class of spaces where swapping open and compact saturated sets gives you another space in the same class, then we would get two theorems at the price. And let's see if, in fact, we have a complete symmetry. Well, not completely. There are signs of a symmetry, but not a full one. For example, in open sets, in a locally compact Howell spaces, open sets are closed under finite intersections. And similarly, compact sets are closed under finite unions. Likewise, open sets are closed under binary unions, and compact sets are closed under binary intersection. Intersection of two compact sets is compact. But this is not the case for nuller unions and nuller intersection, by which I mean that the empty set is always open, but the whole space may fail to be compact. So there is not a full symmetry. And the idea would be, if you want to get to a full symmetry, either we restrict the class of spaces that we consider, or if we want to cover also non-compact space, we weaken a bit our assumptions on topological spaces. For example, allowing the structure that we consider, what we consider open, not to include the empty set. At least for the purposes of what I'm presenting today. Okay, I want to reinforce the fact that we really have, although not a full symmetry, an almost full symmetry, a partial symmetry. And for this, let's see the very definition of compact sets. Maybe the one you're more familiar with is the following. Subset K is compact. Equally, for every family U of open sets, K is covered by the union, then there is a finite subcover. Okay. Okay, there's an equivalent statement. So if you suppose that the family is closed under finite unions, here, instead of having finitely many open sets, you can just take one. And in fact, an equivalent formulation of compactness for K is that for every directed family of open sets, now directed means that there are at least one open set, and every two open sets in the family have a common upper bound in the same family. For example, if your family is closed under finite unions, you have a directed family. So directed means that every finite subfamily has a common upper bound in the family. For example, you can think of a chain, an unempty chain of opens. Okay, if you have a directed family I of open set and K is containing the union of these opens, then there is an open in the family such that K is containing U. Okay, so this is an equivalent formulation of compactness for K. That if a directed family of open sets covers K, then already one of the open sets in the family covers K. And if we swap things around, we replace open by compact, get a property that actually holds in every Hausdorff space. Now, instead of having a directed family of open set, we have a co-directed family. So an empty family where every two compact sets have a common lower bound in the family. Now, for every co-directed family of compact sets, for every open U, if the intersection of the compact sets is contained in U, then already one compact in the family is contained in U. Okay, so Hausdorff spaces satisfies this statement. In fact, also all sober spaces, if you know what sober spaces are, but here instead of compact set, you should use a really compact saturated sets. So the compact set that are intersectionable. And that is to say that, in fact, already in Hausdorff spaces and in sober spaces, we have strong signs of this symmetry between open sets. Because they satisfy both the statement above, that for every compact set we have this implication, but also the symmetric state. Okay, and the reason why I got interested to this is that it's because of stone duality. Stone duality is, here duality means categorical duality. Stone duality is a categorical duality between stone spaces and Boolean algebras. In essence, you can think of it as a way to represent Boolean algebras. In this representation, given a stone space, you can take the set of subsets that are both closed and open, or equivalently both compact and open in this case, and you get a Boolean algebras. And this gives out one-to-one correspondence. If you don't know what a stone space is, not so important for this talk. And Stone generalized this to a duality for what are called the bounded distributive lattices, which are one-to-one correspondence with the spectral spaces. Again, if you're not familiar with them, doesn't matter. But the idea is that you get a bounded distributive lattice by taking the open compact sets of a spectrum. And in both these classes, the symmetry is between open set and compact set is perfect. And this is because just like categories have have this self-symmetry that given a category, you can consider the opposite and it's still a category. Something similar happened here. For a spectral space X, I can build sort of a mirror space where the open sets of this new space, called the Gros dual, are precisely the complements of the compact saturated set of the space you start with. And vice versa, the compact saturated sets of the new space are the complements of the opens of the old space. And this is still a spectral space, and applying this process twice gives you back to start with. Let's see an example. Okay, consider this space here. This space, you can see it in 0, 1, 0, 1/2, 3/4, 7/8, and so on, and at the end you take 1. Okay, this is a spectral space when you keep it with the upper topology, with the subspace topology of 0, 1 with the upper topology. So the opens are things of the form. You start from here and you go there. And here the compact saturated sets are the same thing, but they are, let's say, closed upsets of 0, 0, 1. And if you take the space, the Gros dual, the space associated to this, it's the same set, but now the opens are the open that are downward closed. So the topology you get when you keep it 0, 1 with a lower topology. Okay, the two spaces are not isomorphic, but we have an involution on the class of spectral spaces. And if you know about the distributive lattice, this involution corresponds to the fact that if you take a bounded distributive lattice like this, you can flip it, you can put it upside down, and you get another bounded distributive lattice. Doing this process twice gives you back the original lattice. All right. So in spectral spaces, we have this complete symmetry, but one other categorical duality I was interested in is the one between sober spaces and spatial frames. And sober spaces are certain topological spaces, and what's interesting about them is that they can be recovered from the poset of open sets. So that you have a connection between a point set topology and point free topology. And here, sober spaces have signs of a partial symmetry just because they satisfy that condition, the dual condition of the definition of compact with the co-directed sets. But it's only a partial symmetry. For example, the empty set is always open, but the whole space may not be compact. And since there's this strong signs of symmetry, I wanted to know, can we embed this duality into something where the symmetry is complete? And to do this, what we need is a setting with a full symmetry between openness and compactness. And we need a sort of equilibrium, because we want something that is general enough that covers all sober spaces, but also restricted enough so that we get some theorems about these things. In particular, I wanted to still keep a stone-like duality. And what's interesting to me is that one such equilibrium exists. And this is what I want to present. Before stating the definitions and the main results, I'll tell you why why I've been interested in this. And one of the reasons is what I said before, that if you have symmetry, we have two theorems at the price of one. Moreover, I wanted to know whether also distributive lattices that are not necessarily distributive bounded can be represented in a way using open compact sets. And with the usual definition of topological space, let's say one difficulty is that the empty set is always open and compact. So although there are representation of distributive lattices, none of them can be obtained as compact open with a usual definition of topological space. And moreover, I think that preserving this symmetry in constructions and definitions gives you some guidance on what are the right constructions, right definitions, and proofs. And finally, there are two, let's say, very personal reasons that maybe, well, are personal. I don't know if you will share them or not in this case. One is aesthetic. I felt that, okay, would be beautiful to have to complete this partial symmetry to a complete symmetry, and one is that this allowed me to understand better why certain theorems appeared in a certain ways with certain hypotheses. All right. Nonetheless, there is a small price to pay. That is that we have to take the definition of open and compact as both as primitive. Okay, that is because already in Hausdorff spaces, compact sets do not determine the open sets. There are on the same set, I can put two different Hausdorff topology with the same compact sets. So if we want to cover all the Hausdorff spaces and have this symmetry, we have to take both as primitive notions, because otherwise compact sets are determined by open sets, but not vice versa. So we will consider space-like objects which consist of a set and two families, one of what we consider compact sets and one of what we consider to be open sets. And they interact with some of the usual properties, but they're not determined one from the other. Of course, then one can restrict to classes where they are determined one from the other, but in general, they're not. Okay, so which closure properties survive? So in Hausdorff spaces, or actually in sober spaces, finite intersection of compact saturated sets may not be compact. And symmetrically, so we have to abandon the requirement that, at least for our purposes, that open sets are closed under finite unions. But what survives is this, that in all sober spaces, compact saturated sets are closed under co-directed intersections. While maybe they might not be closed under finite intersection, if you take a compact co-filtered co-directed intersection of compact sets, it's still compact saturated set, it's still compact saturated. And so we can keep this requirement that K is closed under co-directed intersections, and dually that the opens are closed under directed unions. And this is great because directed unions are those that allow us to state what is the relationship between compact sets and open sets. All right, one last thing before the main definition. Yes.
Yeah, you are sacrificing Hausdorff as the openness.
Sorry?
You're not using Hausdorff does for the elements.
Yes.
Second place in Hausdorff.
I don't impose what you consider the space-like object to be Hausdorff, but you can specialize. Sorry. Yes, I mean for symmetry to work. In the old class, yeah, I will. First of all, I consider open set and compact set primitive, and yeah, I don't impose Hausdorffness, so that I don't have also to impose the dual notion of Hausdorffness. But then at the end, you may restrict to a certain class of Hausdorff spaces, and in that particular class, maybe you don't have symmetry. Or I don't know if I understood your question. But anyway, also in Hausdorff spaces, since in particular they are sober, compact sets are closed under codirected intersections. Now, Hausdorff space, if you take a codirected intersection of compact sets, is compact. But let's say the main reason why I spoke about Hausdorff is because maybe you're more familiar with these spaces. But what I was interested in mainly is to cover sober spaces, of which Hausdorff spaces are a special example. Okay, so given a topological space, we can define a partial order in this space. Okay. When ST1, this partial order is the identity. So for Hausdorff spaces, it's not that interesting. This partial, this pre-order, because it's the identity. But in general, you can define X less or equal to Y if and only if every open set containing X contains also Y. This is a pre-order, and if the space is zero, this is a partial order. And here, if you notice, I draw the open set as an upset, as a set that is closed upwards. Because in fact, in this partial order, this pre-order, any open is an upset. And in general, the upsets are precisely the saturated sets. So the sets that are intersection of open sets. But anyway, when you have T1, this partial order is just equality. Okay, also now notice that open sets and also compact saturated sets are both upsets. So this will motivate why I give the following definition. Okay, that's the main definition of this talk. And that's what we call the chaos space, where K should be reminiscent of compact and O of open. And a chaos space is a triple XKO, where X is a poset. Okay, you should think of the X as the underlying set of your space, and the partial order as the specialization order of the slide before. And now, instead of having just one family of subsets of X, we have two families, K and O, which are sets of upsets of X. Okay, such that certain conditions hold. Now we will go through them. But you may think of these as, actually, let me go to the slide. You can think of these, to simplify things, as the partial order to be, if you start with this Hausdorff space, the partial order to be the equality, and K to consist of the compact sets, and O to consist of the open sets. So now, we require that O is closed under directed unions. Okay. Remember, think of these directed unions You may think of these as chains where all the opens are totally ordered in the family, more or less. In duality, K is closed under co-directed intersections. So if you family that shrinks of compact sets, the intersection would be still we require it to still be in this family, K, that we call of compact sets. And moreover, the important thing is this fundamental relation between compact set. If a compact set K is containing a directed union of opens, then already one of the opens is in the covers K. And symmetrically, if an intersection, a co-directed intersection of compacts is containing an open, then one of the compact sets is containing the open. Finally, we ask that principal upsets for a set, if you look at the things above it, which in this particular case is just a singleton, these require it to be compact. The principal downset we require it to be closed, meaning that the complement is open. All right, so what I like about this definition is that everything is pretty symmetrical, and it has some familiar things as examples. For example, every Hausdorff space satisfies this. For example, these two conditions. Here, the principal upset is just a singleton X, which is always compact. And here, this is the complement of a singleton, which a Hausdorff space is always open. Generally in T1 space. Let's say a bit more sophisticated example is any sober space. If you're familiar with it. Then in this case, lesser equal is the specialization order. And you can take as K the class of compact saturated sets. Those compact sets that are intersection of opens. And so since here these notions are all symmetrical, if I have a chaos space, then I get for free another one just by reversing the order. And as new compacts, I declare as compact the complements of the open in your chaos space, vice versa. Declare the opens new chaos space to be the complements of the compacts. And applying this twice gives you back the same chaos space. So if you prove something for chaos space, then you get automatically a dual statement. All right. Or as another example, we can take R with its usual order and as class of compact, all things of this form, the interval from A to infinity, together with the empty set. So we need to take the empty set because we want compact to be closed under co-directed intersections. So if we intersect these intervals going upwards, get the empty set. And the open set, we can declare them to be those of this form. So A to plus infinity, together with R. Because we need to take R because we want our opens to be closed under directed units. All right, and the reason why I got interested in these chaos spaces is that they can be captured by some point-free object, namely given across space, a chaos space, and forget the points, and just remember what we the set of compact sets, the set of open sets, and the relation of inclusion of a compact set, from which, by the way, you can recover the inclusion order both on K and on O. And so you can treat this triple two sets in a relation between them abstractly, just like you can replace a superspace by its frame of opens. But now here we have two sorts. All right. Okay, and this is the main result. I will not spell out all the details, which, if you want, are on our archive preprint, but just give you a flavor of what it is. The main result is that the category of chaos spaces, certain appropriate morphisms, is dually equivalent to the category of what we call distributive bi-dcpos. Well, if a chaos space is something is a triple of this form, a space into family of subsets, a distributive bi-dcpos. Instead of whereas frames are just a partial order with certain properties, here we take two sets, K and O, and a certain relation, which models the inclusion of a compact one open set. And we require some properties on this triple. And the interesting thing is that there's a one-to-one bijection between chaos spaces and distributive bi-dcpos. All right. Yeah, we're not going to the details, which are on archive or some backup slides. But let me tell you that some sources of inspiration have been by topology, formal concept analysis, true spaces, canonical extensions, if you're familiar with any of it, and domain theories and DCPOs. All right. So finally, let's say the picture I want to convey is that we have this duality between several spaces, spatial frames. This is well known. What we develop is this duality between chaos spaces and distributive bi-dcpos, where both of these have a symmetric flavor. Here in the style of the Gros, and here in the style of Lawson duality, if you've ever heard of it. But anyway, the main message is that this duality embeds here. And the main feature of this is that we have a complete symmetry between compact and open. All right. So, well, some more details you can find on the archive preprints. And with this, I would like to